welcome everybody. In this video, I'm going to continue the discussion on what is simulation. These notes are based on the book Simulation with Arena in Chapter 1 and some of my own contributions. In the previous video, we were discussing the advantages of simulation, and we can account for many. One of them is the capacity to construct complexity, no matter how difficult it is. We can represent an accurate model of reality. We have also the ability to represent uncertainty and non-stationarity, which means we have stochastic events that could affect the system, and also not the performance of the system is stressed by external factors that change through time. More to the advantages of simulation, we have the fact that computing costs have been reduced. As everybody knows, in the past, large computers used to fill complete rooms, and they were not as powerful as our laptops or our current cell phones. So we have much more powerful devices now, with also importantly with large amount of memory, and that gives us the opportunity to create more sophisticated models. Currently, we have simulation software that is far easier to use because they have graphical user interface, and that the fact that we have a lot of memory is not a restriction on how large our models can be. We also have embedded in the programs, in the packages, the capacity to do statistical analysis and analysis of the operation for improvement. So those are advantages for modeling more complex systems. Bad news about simulation is that these are just approximation, because we have to acknowledge that the possible events in nature vary enough for us not to be able to account for all the possible combinations. So we draw estimates, and it's a sampling process. In that sense, we input in the system random events, and we get random stochastic output. And that comes with issues about noise control and the capacity to replicate the performance of the system, because we may find that in the computer we found an event that was very unlikely, but nonetheless in the simulation process happened. Does that really mean that that is going to be a recurrent problem, or is that just something that by a very unlikely combination of events, it happened in our simulation? We have the problem of sequential sampling, and sequential sampling has the problem of autocorrelation, where data is not independent and it's difficult to actually generate valid conclusions about the real performance of the system. And we can exploit the different variance reduction techniques. So all this happens in the context of a better understanding of statistics. So for this particular course, that's why you need statistics so importantly. There are different types of simulations. We have static and dynamic simulation. Static simulation means that we do not need to change the model in time. We just create different instances of the problem without seeing the dynamic change through time of the system. So whereas a queuing model or a manufacturing logistics system that depicts the traveling of the trucks and the movement of the product in the warehouses and so on, that would be a dynamic system. A static system would just represent, well, what are the chances of something being in a particular state? And we can still generate a large number of samples to verify how risky it is that we fall in that particular situation. That would be static versus dynamic. Continuous change versus discrete change is how we handle the clock inside the computer. In a continuous change, the clock just advances every so often, regardless if there is an event to be accounted for or not. We progress the clock in discrete intervals, depending on the nature of the simulation. Could be a fraction of a second, it could be a second, it could be the internal this is the clock in the internal representation of the model. In other words, the computation might take just a fraction of a second, but the unit could be a month. So that computation of what would happen in the next month, and you're planning to model maybe 100 months, would happen very fast in the computer. So the continuous change refers to increasing by the same amount of time, whether if it's 1 second, 1 week, 1 month, the internal clock in the model. Discrete change means that we will change the clock only to the next event. So sometimes if the next event is within a couple of minutes, we represent the next 2 minutes. But if the next event after the third event happens, say 7 minutes after the second, if the third event happens 7 minutes after the second, we don't need to represent any one of the minutes or anything in between minute number 2 and minute number 7. That would be the discrete change simulation. Deterministic means that all the variables are represented in such a way that there is no probability associated to the event. The stochastic refers to the fact that some of the events have to be represented in terms of probabilistic events. And therefore, some of the description of the simulation types that we have include dynamic, discrete, change, and stochastic. These would be the ones that we are going to be considering when we use particularly ARENA. During the course, though, I am going to explain a little bit of how to use the inner workings of all these techniques in order to be able to create your own customized models when using ARENA is not the right answer. In the book, you have a problem that is represented by the throwing of a needle to try to compute pi. I will now proceed to try to make a similar attempt to compute pi, but I will use Excel instead of throwing a needle. The needle problem would be doing an iconic or physical model. I will use a logic or mathematical model. Consider a circle that is circumscribed by a square. The square holds the circle right on the edges, and the radius of the circle is 1 unit. And with this circle of 1, the square measures 2 by 2. And the question would be, how can we use this to figure out pi? If we were to drop ink droplets on the paper, many of them very small, and we quantify how many of these droplets are in total and how many of them fall inside the circle, then we can create a ratio of how much the area of the circle covers the square as a percentage, because there's an estimate, not precise, but an estimate would be that the same number of droplets that we have covering the circle divided by the total number of droplets covering the square would account for the area of the circle as a ratio of the area of the square. And with that, since we know that the area of the square is 4 and the area of the circle is pi times r squared, then we can compute that ratio of the square as pi squared times r divided by 4. But 4 is nothing but 2 times r, so that's how we arrive to the 4, and r is in this case 1. So we can cancel r, and that ratio that we get, it's equivalent to dividing pi divided by 4. That's how we get the ratio. So doing the algebra, if we multiply this ratio times 4, we would get an estimate of pi. So let's do that in Excel. Very good. So we have here my Excel spreadsheet, and I'm just going to begin to create points. To create random points, I have here the number of the points, the number 1, number 2, number 3 point. And then, since I don't know where this ink dot is going to fall, I am going to generate a random number associated with the X value, the X position, another random number associated with the Y variable, Y position. Now, if we look at the this problem here, it'd be convenient for our center to be at 0, 0, and therefore the values for X should go from -1 to +1, and the values for Y also from -1 to +1. So we need to modify these numbers because at this moment these random numbers fluctuate from 0 to 1, and we want the position in X to be from -1 to 1. And the transformation that we need to operate on the random number will be the random number times 2 minus 1. And now I will have numbers that fluctuate from -1 to +1. And just to demonstrate that, let's do these 4 points. So now you can see that the numbers are fluctuating from -1 to 1. And now we need to compute if this combination of XY points are within the circle or not, and we need to count them. We know at this moment we have 4 points, but we need to know if all of these are inside the circle or not. So what we do is use the equation for distance, which is x squared plus y squared all that we're going to compute the square root of all that. And the distance, the numbers keep fluctuating because it's prepared as random. But you see, this particular point is out of the circle, one radius of 1, and therefore that would not be in the circle. So we can use a formula if this distance is less than or equal to 1, then we will count it as being in the circle. Otherwise, if it's larger than 1, we will count it as being out of the circle. And this number will keep fluctuating every time we compute the spreadsheet. Right? So now we have a problem because, of course, maybe 4 points are very few points. We would have a more accurate response if we had a larger quantity. So instead of having 4 points, I am going to run this simulation with some 500 plus points. Let's see, 543 points. That should be more accurate. So this is the distance to the origin. This is the question, or if it's in circle. And now we just need to add how many of these points are in the circle. 447 out of, we can count how many points in total. We have 543, so the ratio is 427 divided by 543, and in order to compute pi, this number would be 0.81 times 4, right? And the estimate we get is 3.07 for that ratio. And again, this is just an estimate. Of course, if I take another sample, you will see the numbers keep changing, fluctuating around the true value. Very unlikely you will get any 2 point something or 4 point something. The numbers fluctuate around the true value of pi. And this would be a modified problem like the ones you saw with the Buffon as it's explained in the book. So as just similar as what it's stated in the book, this problem experiment was performed in 1733. Now with the computer I can use Excel, and of course I don't need to, it doesn't take me that long to make that many samples. But we have similar conclusions about how to run the experiment. First, we need to run experiments in order to compute the results that we have. Similarly, in simulation, we will have to compute several experiments. Computing just one circle did not give us the right answer, so we need, in order to estimate a better result, to compute more than one circle. We also depended on randomness, which gives us the benefit of not having a predetermined location for the points, making it this more independent, a true experiment that it's independent from the perspective of the viewer or the user. We have the capacity to run replications, and the replications, the more circles we do, we reduce the error, because we can compare what was the result in the first circle for pi, and then what would be the next result in the circle for pi, and then we can compute just an average of those, and the large numbers will compare, will cancel out the smallest numbers, arriving to a closer true value for pi. Finally, or including, we would have a sampling process and control error, in which until we find that this error is small enough, we would need to keep asking for more samples. Also, we would try to come up with a faster set of responses we did that by including more points, but there are other options also that we will discuss in order to reduce the variability and get to fast responses. I am going to stop this second video here, and I will start a third video on this same topic of introduction to simulation in the next one.